Hold on, give me 1 minute. I got some some stuff going on. I'll be with y'all shortly though, I promise. All right, thank you for your patience. Won't waste any time talking about that. So let's just go ahead and start talking about our whiteboard so we can get into the material. And again, thank you for your patience. So we have our usual list of Mymathlab assignments here. We got one due no later than tonight, 2.4. We got 3.1 and 3.2 that are going to be due the following class day, the 24th. And then 3.3, which will finish today, will be due in a week. That'll be due on the 29th. We have our Excel 2.1 currency that's due today. I'm assigning the next one, which is 2.4 CPI. That will be due in 1 week on the 29th. We have a discussion board previously assigned due today. We have another discussion board previously assigned due on the 24th. Remember that one of those everyone has to participate. I made it so that even if I had 2 billion students, that last 2 billionth student would be able to participate because we just keep extending the dates and extending the dates and extending the dates inside of the assignment. And I don't mean a due date. I mean, we're talking about dates for something that or no, I'm sorry, it was ages. It's ages. It was like 25 and then 30 and then 35 and then 40. I'm thinking of a discussion board that's coming up later. All right, we have a quiz that's due today. Remember, that's a 2-question quiz. Make sure to pay attention to the instructions. We already discussed that. And then I'm assigning another quiz today that is literally titled Pay Attention. You can find that one in Canvas immediately below the page 101 quiz. The one thing that I want to make sure to point out is don't answer, I say to answer it as a QR student, to answer it in a good way, but I don't want sentences, I don't want paragraphs, I just want a number, or I just want a word, or I just want a number and a word. So maybe the answer is 5, or maybe the answer is glasses, or maybe the answer is 5 glasses. So that's what I mean by that. So maybe the answer is just a number, maybe it's a word, maybe it's a number and a word. No sentences, no paragraphs, because when you do that, you will mess up the Canvas algorithm. I won't have programmed in the specific sentence you type and it'll mark it wrong, even if the appropriate answer is inside of that sentence. Now, you might say, well, Mr. Beckner, shouldn't I get full credit for that if I write a sentence with the correct answer in it? And I'm going to say, you'll get a decent amount of credit. You'll get most credit, but you won't get perfect credit because you didn't pay attention to the instructions, something that is a constant struggle with everyone, not just y'all, everyone in the real world, but it's a very important detail because things like this can make critical components of our lives at some point. Let's see, what else? The last thing I need to remind us about is that I will not be hosting a live Zoom on Thursday's class, this Thursday, the 24th. I am going to be putting everything together on Wednesday, and then no later than Wednesday evening, it should be available in YouTube. And of course, I will have the links in Canvas. So when you log in on Thursday, I will have changed the name to the live link saying there's no class on the 24th. So that will be obvious, hopefully. And then if you scroll to the bottom of the lecture videos, you will see the most recent one, the one for the 24th, and you will still be responsible for watching that entire lecture. Do you have to watch it on the 24th? No, just like with our classes that I host live and then put up on YouTube, if you have to catch it a day or two later, that's fine, but don't put it off for a week or a month or a year, especially the year one. Month, we'll be pretty much done at that point anyways. I do want to point out that we're going to talk about some very important stuff in that lecture that's going to go straight to YouTube, straight to VHS, right? Straight to DVD. We're going to be talking about how the midterm is going to work. We're going to talk about how the project is going to work. So those are going to be two very, very, very important details to check that video out. And then by the 24th, actually, I think I've already made them live. You can go ahead and find the document for the project inside of Canvas. But again, I'm not going to talk about that at all until next class, which again will be completely words are hard. That will be completely pre-recorded, unlike the normal lectures where I use a mix of live and pre-recorded material. But with that being said, let's go ahead and pick up where we left off. We're going to get into 3.3. And here we go. Actually, I need another minute. I have some chaos going on at home, and I really can't control it. So just give me 30 seconds. Sorry, everyone. All right, here we go. And this is exactly why I like to use some pre-recorded material because of this stuff.
3.3, a longer section. And yeah, I don't need to say and. Rates. We have talked about rates lightly already. When we talked about miles per hour, we said that that was a rate. We've talked about the word per many times already and how it means that the next unit goes in a denominator. So those things were rates, and we're going to start studying them a little more explicitly. We're going to talk about ways that we can effectively use rates like in the grocery store to do a cost analysis. Not necessarily just in the grocery store, you can do it anywhere. But that's one of the things that I would love for you to take away from this course, not just because it's cool math, but because it's something you can use every day. If you want to say, all right, I got this brand of candy versus this brand of candy, and I want to know which one's cheaper. Well, okay, well, this one is $3 and the other one's $4, so obviously the one that's $3 is cheaper. Well, not necessarily, because maybe the $4 one you get a pound of candy and the $3 one you get 2 ounces of candy. So yes, it's going to cost you less to buy the $3 thing versus the $4 thing, but you're going to get proportionally more with the $4 thing, or more than proportionally more, in fact. So it would make it more cost effective. Or maybe you go, okay, well, I really like Chick-fil-A sandwiches and I eat one every day and it costs me about $4 after tax. Or so one Chick-fil-A sandwich is $4. So on Monday, you're like, I could go to the grocery store and buy a bunch of chicken and make this for the week. I found this recipe on YouTube to, I got the pickle brine, I got the breading, whatever, all that jazz, the peanut oil. And you say, okay, well, I could just do this at home. Maybe that'd be more cost effective. You go, well, no, if I go to Chick-fil-A, it's going to cost me $4 for the sandwich. But if I go to the store, I got to buy 2 pounds of chicken breast. And that's going to be, I don't know, $9 or $10 unless you're buying the super cheap stuff, which is fine if you are. Maybe it's only $5. And then you got to buy buns and you got to buy the pickle brine and all that other stuff. So you go, well, no, it's cheaper to just buy the $4 sandwich. But then on Tuesday, you got to buy it again. And on Wednesday, you got to buy it again. On Thursday, you got to buy it again. And Friday, you got to buy it again. Whereas if you made 5 of these all at once on Monday and froze a few so that your chicken doesn't go bad, okay, yeah, it might have cost you like $12 or $13 to buy all the ingredients and stuff, but it's going to last you 5 days. versus that sandwich that's $4 only going to last you one day. So yeah, it's going to cost you less on Monday to buy the $4 sandwich instead of the $12 of ingredients. But by the time Friday rolls around, you're going, whoa, I'm spending more money. This actually does suck. I should have bought the stuff myself. Whatever. Okay, so rates are a ratio of two different types of quantities. So rates have to be two different types of quantities to call it a true rate. Now, yes, in the world, you can call a rate a ratio of two of the same thing, and you can let that slide in the same way that when I say it's 72 degrees outside, that's not technically correct. It's 72 degrees Fahrenheit outside. So when we talk about rates in the classroom, we're going to talk about them being different units, comparing apples to oranges, comparing students to teachers, comparing distance to time, comparing miles to hours, comparing feet to seconds, comparing kilometers to days. And all of those last 3 or 4 that I said are actually the same thing. It's just that one I labeled with actual dimensions and the other I labeled with their literal quantities. So distance and time would be the actual quantity types, whereas miles per hour or feet per second or kilometers per day, those would be labeled with units. Now, it doesn't matter how you label them as long as you give them an accurate label that you can use and repeat accurately. So cost analysis can be as simple as a rate. And that is the problem that we're going to work through here. Cost analysis. Cost analysis is a rate. It's a rate of two different things. It's a rate of, well, the cost, I feel like that's obvious, to how much you get. Cost analysis is a rate, it's a ratio, it's a fraction of cost to how much you get. So if you pay $10 and get one item, then that ratio would be 10 over 1, and it would be $10 per item because you'd have to have all those units in place. But if it costs you $10 for 10 items, then that means that it would cost you $1 per item. So maybe at the store, they've got this super, super high quality product and it costs you $10, and in that thing you get one of the items. And then you've got your much lower quality but still functional and usable item that you pay $10 and you actually get 10 of them in the package. So the first thing would cost you $10 per item because it costs you $10 and you get one item, whereas the second thing, the cheaper thing, ultimately, would cost you $1 per item because it's a $10 cost divided by 10 items. 10 divided by 10 is 1. So that second thing would be more cost effective because you can get 10 of them for the same price that you can get one of the other thing. Now, when we talk about how much you get, you can talk about this in, maybe it's the number of candies, maybe it's the weight, maybe it's based on the size. It just depends on the context of the problem. Now, what's cool is a lot of grocery stores actually put what we call a unit cost. Let me give myself a little more space here. Select, boom, here we go. Come on, thank you. So this is what we're boiling down to. Cost analysis is taking the cost and dividing by how much you get. Unit cost is the cost divided by how much you get. It's the cost per item, or the cost per gram, or the cost per maybe square foot, if you're talking about buying floor tiles, something like that. Relevant to my life right now. So that's unit cost. Now, in the previous example I just verbally went through, we had one item that cost $10 and you got one of them, and then we had another package of items where it cost $10 but you got 10 of them. So the first thing costs $10 per item, the second thing costs $1 per item when you do that division. Which sounds better? Well, the $1 per item. You want this as low as possible. Your goal to be cost effective is that we want this as low as possible. So if we're comparing two products, whichever one is lower is the better unit cost and the better buy. Now, I'm not talking about quality of the item. I'm not saying that the thing that you got 10 of, they're not just going to break almost instantly and maybe you should have just bought the more expensive item. I'll find that if you're going to do any kind of plumbing, metal costs like 2 to 3 times as much as plastic, but you're going to break that plastic 6 to 12 months later, especially if you got kids. So you buy the more expensive item there, unless you just want to keep replacing it. But a lot of people don't have those options or just need to keep things as cheap as possible immediately. I don't know. Doesn't matter. Okay. Bulking on a budget. In fact, let me just do this. Let me bump. Will that move? Yes. Good. Good, good, good. Good. And the answer displayed. Bulking on a budget. You are trying to gain muscle mass, so you want to increase your protein intake. So you're going to the gym, you're lifting weights, but you can't just lift weights, you've also got to eat. And one of the main ideas to gain more muscle mass, besides ripping your muscles and letting them repair over time, is to increase your protein intake. So more protein, more muscle tears, more bulk. So you go to the local grocery store and you find one of those big jugs of whey powder, and the sticker price on it is $20 and it costs 32 grams of protein. And I did go to Kroger recently to research this. And it's $20 and it has 32 grams of protein per serving with 12 servings total. So this is scenario A. You can buy a big jug of powder and that jug is a $20 sticker price. And there's sales tax involved. Let's ignore the sales tax. Let's pretend that we're in Alaska or Oregon, or there's 3 other states, but that's not the point of the problem. So we're in Alaska. Yay, Alaska. So $20 gets you your protein, and in that protein you get 32 grams of protein per serving. So there'll be scoops. You do 2 scoops, and that's 32 grams of protein. And there's 12 servings in that container. So it's not saying that there's 32 grams of protein total. It's saying that there's 32 grams of protein, and then there's another 32 grams of protein, and then there's another 32 grams of protein, and there's 12 of them in total. If you measured them out exactly, you would get 12 servings of this 32 grams. Second scenario is you find some soy protein bars. So we got whey protein and soy protein, and we're not getting into the science of whether whey is better than soy or vice versa. I'm just mentioning that these are the typical products. A lot of protein bars are soy. There are whey protein bars. There are other protein bars out there that aren't whey or soy that you can actually get egg protein and animal protein, things like that. But again, not the point of the problem, but nutritional information, very important. Study it in another class. And I would love to teach a little bit of that, but that's not what I have my degree in, so I don't. So you find these soy protein bars that cost $8. Oh, wow, I'm going to buy those, right? Because 8's cheaper than 20. So when I'm thinking in the moment, 8's cheaper than 20, let's go with the protein bars. Well, hold your horses. Let's think about this mathematically. So with these protein bars that you're paying $8 for, each bar is 20 grams per serving or per bar, whichever way you want to phrase it, and there's 6 bars total. So each bar, each serving has less protein, but you could always just eat like a little bit of a second bar if you wanted exactly 32 grams, or maybe from the whey protein, you just scoop a little bit less and you try and measure out 20 grams of protein. Again, the delivery is not the point of this. So if all you care about is getting your protein as cheap as possible, which do you buy? So all we care about is getting it as cheap as possible, not about getting 32 grams versus 20 grams, not about whey versus soy, just cost analysis, pure, unadulterated cost analysis. So you want to keep this ratio of cost to grams of protein as low as possible. Remember, unit cost is the cost at how much you get of it. We don't want to compare the cost to the total weight in this instance because we don't care about the total weight of the product. We don't care how much fat or how much carbs are in this. We're only caring about the protein here. So you wouldn't want to just compare it to the pure weight of it. You would need to go specifically to the weight of protein. Now, maybe you're thinking, I just want as many calories as possible, and then you could just go strictly to the weight, or you could go use calorie numbers. The weight number is arguably not valid for calorie consumption as well, because you can have empty, I don't want to say empty calories, but weight that doesn't actually produce the same number of calories because they're not distributed evenly. Science, because science, that's all. So you would just use the calorie number instead. So you'd go cost per calorie, but we're going to go cost per gram of protein. But there's a problem here. How much protein do we actually get from each item total? We don't know. We weren't told. I told you get 32 grams per double scoop of protein powder. I told you you get 20 grams of protein per bar. But how much protein is in the package of bars? How much protein is in the container of powder? Because it's not just one serving. It's not just 32 grams. There's 12 servings. It's not just 20 grams total in a single bar. There's 6 bars in total. So you've got to do some math. Now, some people will automatically know, oh, you need to multiply the 32 and the 12 and the 20 and the 6. But some of you might be thinking, well, maybe I need to divide them, or maybe I add them, or maybe I subtract them. So here is what opens an entire world of mathematics that we already started with dimensional analysis. It's the idea of, I think I might have said this in the past, math on the back of a napkin. If you can take some numbers and with units, multiply and divide them in such a way that the answer you get has the units you need, the answer is probably right. And that seems extremely far-fetched, and yet there are entire books of mathematics written on that. So just think about taking, for the powder, caps on clearly, the total grams of protein should be equal to. So the two numbers we're dealing with for the powder, let's highlight it for now, are the 32 grams per serving, and then it's 12 servings total. Those are the two things. So what I'm suggesting to you is that if you can write these numbers with their units in appropriate places and multiply or divide them in such a way that the answer has the expected units of what the answer is, then you're good. So let's see, 32 grams of protein per serving. Let's just write that. 32 grams of protein per serving. The word per means it goes in the bottom. So it's grams per serving. The word per here is extremely important. I've said it many times. I've written it at least once. Per means the next unit goes in the bottom. Then we have 12 servings. Now, if you try to divide this, it would look really weird. So let's try multiplying it. I say it would look really weird, and you would end up with grams per serving squared. And that's the same idea as we saw in the very beginning of 3.1. I don't want to do that just going around in a circle twice, though. So if you take the 32 times the 12, you'll get a number. And it's 384. Now let's see what the units do. We have the grams. The grams are still there because it didn't cancel anything. We have a serving and a bottom and a serving and a top, so they cancel. So the total grams of protein is 384 grams. This unit is the expected unit of the answer. There's no serving written anywhere. 384 is an answer that makes sense. If it's 32 grams per serving, you could literally just count them out. 32 for the first, 32 for the second is 64, 32 for the third is 96, and just add up 32 12 times until you run out of powder and you get 384 grams. So again, this idea here, that if you just multiply or divide numbers with units in a way that your answer has the units you'd expect and the number makes sense, it's probably right, and this is definitely right. So that's the total grams of protein. There's 384 grams of protein, and we don't have to do them 32 grams at a time. We could measure out 20 grams of protein. We could measure out 15 grams of protein. We could eat half the jug in one sitting if we really wanted to, and get about 200 grams of protein. What's that, 198? I'm sorry, 192. I don't know why I said 8. 192. Okay, so then the unit cost be equal to, we take the total cost, which is the $20. We divide it by where is it? How much we have, which how much we have is 384 grams of protein. So we take 20 and divide by 384. 20 divided by 384. And we get 0.052 blah, 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 blah. Now, this, you might say this is a cost, so let's just round it to 2 decimal places. And I will say that usually works. But if two things are really close to unit cost, you may actually have to go to 3 or even 4 decimals to see which one's cheaper. But this answer, spoilers, it will be good enough. So it was 0.05. And now you could write it this way, but it just looks a little weird. So let's write it as 0.05 per gram of protein. This is just laid out a little better. So that protein powder, when you boil this thing down to just 1 gram of protein at a time, it's costing you about 5 cents per gram of protein. Well, now let's try out the, oops, spoiler alerts. Bars. We got to find the total grams protein. And we already saw what to do, so we're just doing the same thing here. It was 20 grams per serving. Per means it goes in the bottom. And then times how many servings? Well, we had 6 bars. Now, I don't want to write servings in the bottom and bars here. Use your words consistently. So if you put 20 grams per bar and then times 6 bars, you'll see the same cancellation. Cancel, cancel. 20 times 6 is 120. Not going to pull out the calculator for that. The only units you have left are your grams. If you had 20 grams per bar, 20, 40, 60, 80, 100, 120. The answer makes sense. Giving us a unit cost of, you take the, how much did we pay for the bars? I think it was 8. Let me confirm. Yes, it was $8. That was the total cost. And then per, so 120 grams of protein. And when we do 8 divided by 120, 8 divided by 120, 0.06 something, 0.0666666, which rounded to the nearest penny would be 0.07. So 0.07 per gram, but it's just better written as 7 cents per gram of protein. So again, if you only care about which thing has a cheaper unit cost, which one will cost you less money over a long period of time, you're going to want this one. This is cheaper. So you buy the jug of powder. Now, when you go to the grocery store that one time, it's $8 versus $20. You go, Mr. Beckner, that's not right. I just spent $12 more. But guess what? If you only buy one thing of bars, if you're eating a bar a day, you're going to have to go back to the grocery store in 6 days. Or maybe you're eating 2 bars a day, and then you're going to have to go back to the grocery store in 3 days. And then you're going to pay that $8 again. Or maybe you just buy 5 or 6 or 7 boxes all at once, and then you have that cost multiplied by it. So yes, it's cheaper to buy 1 box of bars versus 1 jug of powder. But if you're on a regimen that you're going to do over a year, maybe you're trying to intake 50 grams of protein with this stuff a day, on top of your grilled chicken and whatever else you're going to eat. If you're consuming 50 grams a day, that cost multiplied over 365 days, you're going to end up spending maybe an extra 20 bucks on the bars, maybe an extra 100 bucks on the bars, but it would be significant. It's not going to break the bank, but it would be significant. So you can take this and you can compare, milk in one thing. So maybe one brand has the milk in a half gallon and the other brand has the milk in only quarts, or maybe one brand of milk has it in gallons and the other only has it in half gallons. And you go, well, obviously the half gallon's cheaper. It's $1 less or $2 less. Well, when you do this unit cost analysis or cost analysis, however you want to say it, maybe it turns out that the larger thing, even though it has a higher sticker price, is cheaper per unit. Now, if you're buying food and you don't eat it all and it spoils and you throw some away, that changes the game. So make sure that you're actually using everything. Don't be wasteful. Someone just pulled up to my house. Give me 5 seconds and make sure I can ignore them. It always throws me off when a delivery person actually pulls into the driveway. It's very unusual. Okay. We are not ready for 3.4. Not even close. That's too far. We're going to go back to the guided activities. You can see there's actually an Excel homework that we're not going to do because it has a lot more answers than usual, I think, that relates to what we were just talking about. We're going to go up to, here we go. This is an assignment that I have alluded to in the past. And again, it's just not enough answers to make a discussion board out of this with a large class. So we're going to work on this together. In 2011, nearly 14 million monthly prescriptions were written for American adults aged 20 to 39 for ADHD. If there were 82,364,000 adults aged 20 to 34, compute the following. The rate per adult aged 20 to 39 with 3 decimal accuracy. Then if we divide 14 million prescriptions by the rate from number 1, what are the units of the answer? The rate of the prescriptions per 100 adults in that age range, the rate of prescriptions per 1,000 adults in that age range, the rate of prescriptions per 100,000 adults in that age range. And then they ask us, what rate do you think is best? Now, this last question is subjective. So it's saying between answers 3, 4, and 5, which one do you like more? So we'll get to that later. In fact, we probably won't. Let's see how far we can get. I might just have to go a little quick. And I'm just going to use my ugly annotation in the interest of time. Okay. So the rate per adult. So first of all, this number right here is our first instance of a goofy number. Why is it goofy? Well, it's goofy for 2 reasons. First of all, this number up here talking about people is 14 million, and then this number talking about people is in thousands. Why did they give us millions of people in one value and then thousands of people in another value? You know why? To mess with us, to make us think and to make us be careful, because that's what the media does. They screw with us. So this is our first instance of inconsistent units between the same type of quantity. I would say normally, if these numbers are close to each other in terms of size, if one's in millions, the other should be in millions. If one's in thousands, the other should be in thousands. The second reason this number, the one I have circled or boxed right now particularly, is wacky, because if I was going to say something in thousands, we normally have like 15,000 or 700,000 or 32,000 or 82,000. We normally don't have 82,364,000. Notice how I said that. Pay attention. 82,364,000. I said the word thousand twice. That destroys people's minds. So you think this number is 82,000. It's not. It's much more than 82,000. So let's just turn these numbers into what they would be without the words millions and thousands. So 14 million would be a 14 with 6 zeros. That's 14 million. 82,364,000, the word thousand says to add 3 more zeros. So it's 82, 364, 000. So really that number is 82,364,000. So yeah, you can say 82,364,000. Nobody likes saying the word thousand twice or the word million twice. It's a horrible idea. It confuses people to no end. So if you want to write a confusing media article, do something like that. So looking at the text, it doesn't look like these numbers are that close, but in reality they are. 14 million, 82 million. No, they're not super close to each other, but I'm just saying they're in the same types of units in terms of size. So they want to know, what is the rate per adult, the rate of prescriptions per adult in the age range? So we're going the rate of prescriptions to number of adults. Rates are fractions of two different types of units. The rate of prescriptions, they don't actually use the word prescription here, which I think is poor form on their part. So the rate of prescriptions per adult. Well, there were 14 million prescriptions for 82 million adults, so that's what they're asking us to do. So 14 million over the 82,364,000. And when you pull out your calculator, when we do 14 million divided by 82,364, everything look good? Yes. We get 0.1699, blah, blah, blah. They say to round this to 3 decimal places. 0.169, that second 9 tells us to round up, which tells this 9 to go to a 10, which says this 6 goes to a 7. So even though it says 3 decimals, oops, I forgot to take annotate. Put the annotate back on. It's going to be 0.170. And that would be prescriptions, because that's the units from the top, and the bottom was adults, so per adult. So 0.17 prescriptions written per adult. So that says if you have a person, there's a 0.17 chance, if you think about statistics really, or probability, that that person has a prescription for ADHD if they are in the appropriate age range. Now again, we're only talking about that age range. Step 2, they say if we divide 14 million prescriptions by the rate. By the rate means that the rate is what's going to go on bottom. From number 1, what are the units of the answer? We're still on annotate? Yes, we are. If we divide 14 million prescriptions, so if we take 14 million prescriptions and we divide it by the rate that we just got, which is 0.17 Rx per adult. So that's 14 million prescriptions. We want to use our units because we're good QR students. And we're going to divide this by 0.17 prescriptions per adult. Now, here's where things get weird. In fact, let me do this in blue. 0.17 prescriptions per adult. So this is a division, the 14 million divided by the 0.17. But the units in the bottom are not just a single unit, it's a fraction. So what we really need to do here is write this in a slightly different way. It might be better to write this as 14 million. I think I have the right number of zeros. I hope I have the right number of zeros. Yes, I do. Prescriptions, and then over 1, then divided by the 0.17 prescriptions per adults. This is a division of fractions, fraction divided by a fraction. You are supposed to be coming in here with the knowledge of how to divide fractions. But you probably want to change this to the old school form of 14 million prescriptions over 1, then the 0.17 prescriptions per adult, which would give us 14 million prescriptions over 1 times, and let me change color to show that emphasis, times, we flip it. The adults go in the top now, and the 0.17 prescriptions go in the bottom. So here's what happens. This prescription unit ends up canceling that prescription unit. The only units you're left with are adults. So whatever this number is, this 14 million divided by 0.17, let's go off of annotate. 14 million divided by 0.17. We end up with 82,352,000. Now, because of this 0.17 being rounded, this isn't exactly it, but it is pretty close. It's about 82.352.941 adults, which again is very, very close to the number of adults. The only reason it's not exactly the same is because we rounded the 0.17. This was rounded. If I left this as 0.1699, whatever the rest of it was, then it would actually give us the exact number of adults. But it's very difficult to use that exact number for obvious reasons. So the rate of prescriptions per adult is 0.17. If we divide, we end up canceling the prescription units and getting the number of adults. So what this shows is we took the 14 million prescriptions and the rate, and we did something with them to get an answer, and the answer was something we had already seen. So that these two numbers divided versus these two things but divided, there's a strong relationship. If we had decided to instead, well, what happens if you multiply? If you multiply this 14 million prescriptions by 0.17 prescriptions per adult, you're going to get a nonsense answer. You would get 0.17 times 14 million. You'd get 2.3 million and some change, but the units, you would have prescription in the top twice, so it's prescription squared and then adults. So there's 2.4 million prescriptions squared per adult. I have absolutely no idea what those units mean, so it doesn't make sense. So sometimes you'll be multiplying things together and get an answer that has units that make sense and you're done. If you did the multiplication and you got nonsense units, try dividing them instead. That's that clue of that whole math on the back of a napkin.
All right, just had to swap videos, and we're going to pick up right where we left off with number 3.
So we're starting on number 3. The rate of prescriptions per 100 adults. So we have the 14, I can't see. I've got this cursor over it. There we go. In 2011, nearly 14 million monthly prescriptions were written for American adults aged 20 through 39 for ADHD, and there were 82,364,000 adults in that age range, which we also determined were 82,364,000. All right, I'm going to rehide that and then just use my little piece of paper. Okay, so the rate of prescriptions, which was the 14 million, so the rate of prescriptions was the 14 million. Are X's per, why am I writing it above? The rate of prescriptions, that is not just the 14 million. The rate means there's two things. So it's comparing prescriptions to people. So it's 14 million prescriptions per 82,364,000, and I'm just going to write that number with all the zeros and everything. So this is ultimately trying to reduce this to a per 100. So per 100, if you just do this division off the cuff, what you get is 1, 4, 1, 2, 3, 4, 5, 6 divided by the 82, 364, 0, 0, 0. There we go. And we get 0.17 blah, 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 blah. So I think we rounded that to 3 decimals, which ended up coming out to 0.17. Yes, we did. So that was 0.17, and that would be prescriptions per, and I forgot to write adults. And yes, it's in that specific age range of 20 to 39, but I don't want to have to write all that detail. So 0.17 prescriptions per adult in the age range. But they wanted this to be seen as a per 100. So per 100, a simple way to do that would just be to multiply by 100. And what you would get is 17 per 100. So 17 prescriptions per 100 adults, which is like having 17%. So this would be us scaling a quantity to 100. And you might say, well, how did I know just to do this as a times? Well, I could have set it up as a proportion. So the alternate looking version of this, where you have your 0.17, and that's per 1. So you're going to scale your rate. So the rate is in the top, and then your people in the bottom. And we're going to scale it to 100 instead. So then you have, well, what's the rate per 100? And then you're just cross multiplying, and you can see you're going to take the 0.17 times 100. So again, either way does the job, as long as you don't end up dividing by 100, because then you would have 0.0017 per 100, and that wouldn't make sense. If it's 0.17 per person, if you've got 100 people, that number is going to grow. That's the idea there. So the same thing just keeps going on. So per 1,000, you just take the 14 million prescriptions and divide it by the 82 blah, 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 which ends up being that, that same number, but then you're going to multiply it by 1,000 instead. The same idea, you can set up your proportion and take a long time and get the answer, and you end up with 170 prescriptions per 1,000 adults. If you want to scale this to 100,000 people, well, you take that same division, the 14 million, and you divide it by the 82 million. And that was prescriptions and then adults. And yes, I just rounded the number, but I wouldn't actually use that. Sorry, that got a little sloppy. As I've said before, there's no algorithm making my handwriting better in this, so it looks awful. Even my handwriting is not this bad on a whiteboard. This looks terrible. And then you're going to multiply it, sorry, not equals. Do times 100,000. And some people would have this answer as 17,000. And then it would be prescriptions per 100,000 adults. But the thing is, when you scale to 1 decimal place, when you actually have this division, if you show it, you come off of annotate, 14 million divided by the 82364, 0, 0, 0, and then times the 100,000. There we go. The answer here, because you're multiplying by such a large number, all the decimals that were at the end of that 0.1699 blah, blah, blah number originally now are significant. So it's 16,997.7. Oops, what happened there? Oh. So a more accurate answer is 16,997.7, and that would be prescriptions per 100,000 adults. So number 1, that answer was the 0.17. That was RXs per adult. Number 3, 4, and 5 are all the same concept. We're talking about prescriptions per some number of adults. It's just the first one is scaled to 1 adult. The third one is scaled to 100. The fourth one is scaled to 1,000. The fifth one is scaled to 100,000. Why would any of us do this? Which one's the best answer? That's what number 6 is. And I've mentioned before that this is subjective, which means it's opinion. So one person might think that the first one is the best because it's the simplest, it's less than 1. Maybe they just like decimal values and they like thinking about per adult. Another person might say, well, I like the answer to number 3 more because the answer, since we scaled it to 100, we've talked about how scaling to 100 relates to a percent. So a lot of people like to think of things as percentages. So 17% of adults in this age range are expected to have an ADHD medication. Number 4, people that deal with statistics in media generally would like that one because a lot of the times they'll scale to 1,000 adults, and that's because of this. Whenever you have a really, really, really big number, you get these commas clustering every 3 zeros just for our eyes' sake, for our sanity's sake. But if you do per 1,000, it's basically like you just eliminate having to write 3 zeros. That's the idea of doing something per 1,000. So per 100 is good for percentages. Per 1,000 is just good for taking bigger numbers and getting rid of 3 places. The 5th one, why would we scale to 100,000? Well, when we actually do the division and the multiplication and don't round until the very end, you get what feels like a more precise value. It didn't get rounded nearly as hard as that 0.169 just going up to 0.17 or 17 or 170. It feels like a more accurate value, a more precise value. So some people will like that one and they'll say, okay, well, I'm just going to scale to 100,000 people. I would say I least prefer the last one unless you're going to be dealing with large numbers. If you're going to say, all right, I've got the state of Virginia, which has 7 or 10 million people, roughly 14 million, somewhere in that ballpark. How many people in Virginia do you think have an ADHD medication? If this statistic was true for all adults, not just that particular age range. So if I was going to be dealing with a large number like the population of the state of Virginia, then I would actually like that last one for the accuracy. But if I'm going to go into a classroom of, say, 20 people, and I wouldn't actually ask this, but if I were going to and say, well, what percentage of people do you think in this room have a prescription? So it's not asking who actually has it. I'm saying, what do you think? Well, based on the fact that 17% of people have it, I would just take 17% of the 24 people in class and boom, I'd have my answer. It would be much easier that way. It would be easier to do with the small one. And you could even just use the 0.17. You could take 0.17 times the class population because that's literally the same thing as 17%. 17% is the same as 0.17. It's just anything as a percentage is scaled as 100 people, so it looks bigger. And that's something we're going to study extensively in chapter 4 is percentages as numbers and rates and things like that. All right. So sorry for me kind of stumbling at the beginning, getting the numbers in straight. Like I said, I have some menus up here for Zoom as a teacher that you can't see, and it covers up this entire portion of the screen. So if I cover it, I can't see it. All right, clear. Let's go off of annotate, minimize, scroll down. And I don't want to write on that again. So let's just make a new document. This, do that, sidebar it, boom, there we go. I'm not going to do all of these. I'm just going to do the first 3 or 4. For each question, determine the answer with proper units. The first one has been done for you. And I actually want to go through and do that work anyways. So it says $5,100 divided by $300 per month. I kind of don't like the way they put the dollar symbol after the 300 here, but it's not wrong. It just looks wacky. Usually when people want to put money annotations after, they would go USD instead, unless we were talking about cents, because the cent symbol goes at the end for some reason. So we're doing some multiplications and divisions with units, and there's no need to say very. We've seen many examples of multiplying, especially with the dimensional analysis, that whole out with the old, in with the new. This isn't really out with the old, in with the new necessarily. It could be. This is just saying do the problem, but pay attention to the units. Sometimes they might cancel, sometimes they might stack. Just see what happens. So for number one, again, like I said, we're going to do it anyways. We take the $5,100, and then it says divided by $300 per month. Now, some people might write it this way, and then $300 per month. Remember, the word per always means a division and the thing goes in the bottom. And you might say, well, Mr. Beckner, you already had a bottom. Well, I did, but the thing is, that $300 per month is its own entity. So when I divide by that, it's going to have an extra fraction. And this gets you that compound fraction idea that we've lightly discussed. But the idea is that these two things will be the same. It's $5,100, and then I like to do the division symbol, and then $300 per month. I think this is better because how do we divide fractions? We multiply by the reciprocal, which means flip. That got ugly. We only flip the one after the division symbol, not the first one. So this becomes $5,100, and then I'm going to use red for showing the change, times, and now the month goes in the top, and the $300 goes in the bottom. See, what's critical here is that it's not just the number going to the bottom, it's also the units swapping places, and that looks like I got a Madden drawing. It is not just the number that switches places, it is also the units, which is why it's extremely important to know that the dollars went in the top and the months went in the bottom. Why did I know the months went in the bottom? Because the word per came before it. Easy as pie, easy as per. All right, so let's see what we get. Well, the 5,100 is going to divide the 300 because they're top and bottom of each other. So we'll do 5,100 divided by 300. And that turns out to be 17. Okay, so 17 is our value. But then what about the units? Let's see if things cancel or if they stack, because they could stack. The other dollar could be in the top, and then you've got dollars squared, which would make no sense. Okay, but it doesn't in that case. Dollar in the top, dollar in the bottom, they're gone. The months are in the top, they didn't cancel, so that's why the months goes in the top. So I'm not going to say this is an alternate to number one. Let's just say this is a different problem. Let's say instead of this being a division, what if it was a multiplication? What if it was $5,100 times $300 per month? What would this problem give us as an answer? Would it make any sense? Could it actually be relative to something in this world? Okay, well, the 5,100 times the 300, that's just math, 5,100 times 300, which would give us a big number, 1.53 million. The dollars are not top and bottom, they're both in the top, so they stack, so it's dollars squared. The month is in the bottom. What in the heck is this? This makes no sense. What is a dollar squared per month? In terms of a rational real world thing, it doesn't seem tangible, which means there's probably no reason to be multiplying these two numbers. What is the point of me doing this alternate problem? Again, not an alternate version of the same problem, an alternate problem. It's using the same values, multiplying instead of dividing. The point is that math on the back of a napkin thing I've talked about. There's a whole field of mathematics that basically just say, if you're trying to play with a couple of numbers that have units and rates and all sorts of things, and you're trying to make sense of it to analyze something deeper, whatever, if you can multiply or divide these things with their units and they cancel ultimately to give you something that makes sense, if something just in meters or something that's just in dollars or something that's just in months or dollars per month, something that is a tangible concept, then that means you probably did it right. Again, an entire field of mathematics says you probably did something right as long as the units in the answer make sense. You open up a whole world of mathematics, like talking about how a lot of people know that an ant is 10 or 100 times stronger than its weight. So if an ant weighed a gram, it could lift, let's say, 100 grams. But that's a teeny tiny ant. If you scale that ant to the size of a person, by doing some of this math where you're just multiplying and dividing things and doing some volume to surface area comparisons as well, because it has to do with muscles, it turns out that if you had an ant the size of a human being, it could still only lift 100 grams. It turns out that if you had an ant the size of the Empire State Building, it could still only lift 100 grams. And again, people have showed this argument by just multiplying and dividing things and getting units that make sense. It's not like they have to go develop a random formula for it. Again, literally books written on this. Just try multiplying and dividing things. If you get an answer with units that make sense, then it's a logical answer. At worst, it's off by a factor of 2 to 3. That's about it, the worst thing that can happen. All right, rant aside. Number 2, the one that hasn't been done yet. 400,000 people times 6.2 meters squared per person. So a meter square is a type of area. So this meters squared per person is a population density. It's talking about how much room each person gets. And then it's saying, all right, well, this is how much room each person gets. What if we have 400,000 people? How much room do we need in total? So we have these two figures that someone gives you, and then you go, let's pretend like I didn't actually tell you to multiply this. Maybe you're doing the first thing times the second thing. Maybe you're doing the first thing divided by the second thing. Maybe you're doing the second thing divided by the first thing. I don't need to see say the second thing times the first thing, because that's the same as the first times second. Order of multiplication doesn't matter. So I'm just saying I give you a problem with these two values, and I ask you, well, how much space do they need? This math on the back of the napkin concept just says multiply or divide these numbers until you get an answer that makes sense in terms of units, and boom, there's your answer. So maybe you think you're supposed to divide these things, and if you did that, you would get an answer that wouldn't make sense. So I'm going to do this different problem first, but I'm going to come off of annotate. Clear the screen, off of annotate. So again, different problem. Let's just say again, I gave you a word problem that said you have 400,000 people, and this city or state or whatever on average has 6.2 meters squared per person. And I say, how much space do you need for all these people? Something like that. So all I give you is those two numbers, and you think, maybe I'm just going to divide them. So I take 400,000 people, and then I divide by 6.2 meters squared per, so bottom, person. Now, people and persons are the same thing. People is not persons squared. It's just like having an S at the end of person, persons, people. So you might say, oh, these cancel. Nope, they don't, because this is a division. We don't start doing math with division. We have to change this to 400,000 people, then times persons, aka people, over the 6.2 meters squared. And when you do this, the 6.2 is in the bottom, so we're going to divide. So we take the 400,000, we divide it by 6.2, and that number is, let's just round to the nearest tenth, 64,516.1. 64,516.1. The people and the person, let's just say that's people, so that's people squared. And then on top of meters squared. What in the heck is a people squared per meter squared? That doesn't make no sense. So I could certainly just give you that as a problem and ask you, hey, pay attention to the units, give me these squirrely units in the answer. But again, the point is, you would have these two numbers in the real world in a word problem, something like that, and I don't tell you to multiply or divide them, you got to figure it out. So you go, all right, well, I tried multiplying them and this gave me nonsense. So, excuse me, I tried dividing them and it gave me nonsense. So maybe I'll instead do the actual problem and I'll do the multiplication. Let's try multiplying them. Now again, fair warning, it's possible you need to swap the order of the divisions and that would give you an answer that makes sense. But we're just going to go straight to brass tacks and say that this is what we're doing. The 6.2 meters squared per person, aka people. So now we have people top, people bottom, they cancel. We're going to take the 400,000 times the 6.2. And we get big number, 2.48 million. And that's just meters squared. So that is the answer, and this does make sense for several reasons. Again, the context problem here is you got 400,000 people, and these people are used to having or have on average 6.2 meters squared per person. So in other words, if I put one person in the middle of the field and I say we got to social distance them and they get 6.2 square meters, that means that the area around them, if you took the length times the width, it would equal 6.2 meters squared. So maybe that's like 2.3 meters by 2.3 meters, something like that. Let me get the exact answer. In fact, square root of 6.2. I was really close, 2.5. So basically, you're in a box of a width about 2.5 by 2.5 meters. So again, the problem is, well, how much space do you need for all 400,000 people? First of all, that different problem I made up in us trying to BQ our students in the real world and just having two values and playing with them, it made no sense, A, because of the units. It also made no sense if one person needs, let's just say, about 10 of these meter squares, how do 400,000 people only need 64,000? Because each one person needs about 10, so 10 people would need about 100. That means 100,000 people would need about 1,000,000, which means 400,000 would need about 400 million. Excuse me, 4 million. I said that wrong. I did another factor of 10. And again, that was me just rounding the 6.2 up to a 10. So it's some extreme rounding, which is why 4 million is close to this. It's still in the same order of magnitude, but there is a big difference between 2.4 million and 4 million. But either way, this answer in terms of size, magnitude is another word for size, makes much more sense than 64,000. Meters squared is a measure of area, so the units make sense. So that's 2 check marks for the answer making sense. So number 3. All right, we got 20 miles and 40 miles per hour. So again, this word problem that might relate to it is you're in a car going 40 miles per hour and you've got to cover 20 miles. How long is it going to take you? Maybe that's the problem. Maybe that's the problem. So again, you have a car and you're going 40 miles per hour on average, and you've got 20 miles to cover. How long will it take you to make that drive? In fact, I'm going to type that up for fun. So you're going 40 miles per hour and have to go 20 miles. How long will it take? So this is the real quantitative reasoning problem to number 3, and this is just the math that you end up doing. So maybe you try doing the 20 miles. So again, let's try this. Again, and I'm going to do this wrong. I'm not doing what problem 3 says. Let's say, oh, I think I'm going to multiply these. So you go 40 miles per hour, and you go times 20 miles. Well, 4 times 2 is 8, so you stack the zeros and you get 800. Miles times miles is miles squared. The hours is still in the bottom, and this makes no sense. Okay, so maybe it doesn't work with multiplication, so maybe you try dividing. So the next thing you try is the 40 miles per hour, and you go divided by 20 miles. Well, that's, excuse me, 40 miles per hour times, now the 20 miles was in the top, so it now goes in the bottom. There was nothing in the bottom originally, which means there's a 1 there, which means there's now a 1 in the top. Okay, well, the 40 divided by the 20 in this instance is a 2. The miles do cancel, but look at where the hours are. They're in the bottom, so it's 2 over hours, which means it's 2 per hour. Does that make sense? Is that a time? No, that's saying you're going 2 per hour. 2 what? 2 bobs? 2 oranges? It doesn't say. It's no units. It's just 2 per hour. So no, that actually does not make sense. So the answer is not 2 hours or 2 per hour. So then we do the actual problem. We say, okay, well, the only thing really left to do is 20 miles divided by 40 miles per hour. Okay, so that's 20 miles then times the hours now go on the top, the 40 miles go in the bottom. The 20 and the 40 reduce to a 1/2 or a 0.5 if you do the division. 20 divided by 40 again would be 0.5. The miles cancel, the hours are now in the top, and we have an answer that makes sense. The units are good, which means the number should be good. And it does make sense. If you're going 40 miles an hour, well, 20 miles is half of that, so you should be able to cover that distance in half of an hour, because you would go 40 miles in 1 hour, but you only need to go 20 miles, so it's definitely going to take you less than an hour. This makes sense on all levels. As I've said several times now, this is an unbelievably amazing field of mathematics. It's ridiculously basic, but it can open up so many doors. So this is a skill that I would love for you to all have, but you can't just play with the numbers. You can't just say, oh, do 40 divided by 20 or do 20 divided by 40, because then you might think the answer is 2, which it actually isn't. You go, well, 2 seems like a reasonable amount of time. But again, when you actually play with the units, you prove that the 2 is not the answer, it is the half. And again, you could, if you think carefully, logic your way that the answer is not 2, because again, if you're going 40 miles an hour, that means in 2 hours you would cover 80 miles, because the first hour you'd cover 40 miles, and the second hour you'd cover 40 miles for a total of 80 miles. Amazing field of mathematics. Try it out, use it, love it. There is another field that is inside of this where you do what's known as a volume to surface area argument. That whole fun little ant strength problem is what that's based off of. You can talk about water boiling in a pot based on volume to surface area arguments, because your water takes up a volume of space in 3 dimensions, but your burner is only covering one of those dimensions, one of those surfaces. So the heat's applied only to the bottom surface. It's not applied to the top. It's not applied to the sides. Yes, the sides do heat up a little over time, but really the main source of the heat in a boiling water pot is the bottom of it. The sides just basically heat up to keep the ambient temperature inside. Heat sources at the bottom. So I had a fun little experiment in college where I took 2 pots of water and turned them on. Well, I did all the math first, and I made my argument of whether if you took 2 pots of water or just 1 pot with the entire amount of water from the 2 pots, which one would actually start boiling faster. And I won't say the answer, because that would take all the fun out of it. But I did the math beforehand. I had an argument with an old person over which one was going to be right or wrong. And, well, they weren't as keen to the math of surface area to volume arguments, so they were wrong. I didn't gloat. I might have gloated a little. It's what you do with your parents, right? When you're right, you got to be like, hey, I'm right. Okay. So that, I believe, will close it out for the section. Yes. So let's close. Well, I might not want to close that. Back to this. 3.4. Now, admittedly, 3.4, all the fun, we are not going to do the main idea of this section. I would really want probably 2 full weeks just to talk about dosages of medicine. And it doesn't have to be medicine, but just dosages in general. We usually just talk about it with medicine. This is still the same idea of math on the back of a napkin. It's very similar to dimensional analysis without with the old and with the new idea. The idea with dosage problems, like you've got this much medicine and you need 2 cc's per pound, and you need to administer this much medicine to this heavy weighted person. I'm not saying they're heavy weighted, just like they're 150 pounds heavy, 170 pounds heavy, whatever. How much medicine does that person need if it's a very strict regimen of 2 cc's per pound or a half a cc per pound or whatever it might be. And you can get into all these different conversions and multiplications and divisions, and there can be 5 or 6 or 7 of these products and cancellations. And it's a solid type of problem. It's a great concept. But the amount of manipulation you have to do, just like with those last problems I was doing where I was just taking 2 values and figuring out how to multiply and divide them, in these problems, you end up doing 5 or 6 or 7 of them, and it can be a true struggle of trying to get the setup correctly. You can really circle around the same problem and not get anywhere because you keep trying setups that fail, and you have to learn how to basically predict where to put the next piece of the puzzle. So again, it's solid, but I want to keep being able to do this stuff for weeks on end, and we don't have that time because then we wouldn't get to any of the stuff at the end of the course, which is where my true passion is. So we're going to focus more on the idea of concentrations, which admittedly will never come up again in this course, but it is an awesome type of problem. And then we're going to talk about densities. Densities, which would talk about like you've got this much weight of an object and this much volume to cover it. What's the density of it? So, you know, if I don't want to jump the topic. So concentrations. Concentrations and rates are tied together. Concentrations are a type of rate. But before we actually get into the official discussion of this, let's have some fun. And this problem is a lot more fun when you're in-person class, in an in-person class, especially when I don't actually bring M&Ms to class. That's why I say in theory. So a teacher brings M&Ms to class in theory. So I just gave you all virtual M&Ms. I've got 50 of my virtual M&Ms in the bag, and I'm going to distribute them to 5 students before class. So let's say it's 3 minutes before class and 5 students are in the Zoom call. And I say, all right, for being early, I'm going to take my 50 M&Ms and I'm going to give them to you evenly. So it's not like one student's going to get 7, another student's going to get 12. It's if one student gets 8, the next student gets 8, the next student gets 8. I want to be fair. So what is the rate of pieces of candy to each student? So I'm very specifically asking you for a rate, and I'm telling you what I want that rate to be. If I don't tell you what I want the rate to be, you'd have to say, well, what would the most logical decision be? Would I want to go people to pieces or pieces to people? But I've told you specifically to go pieces to students. So we're going to go pieces to students. That will be our rate. Remember, rates are just fractions with different units. They are ratios. The word rate and the word ratio sound the same. They have the same root word, R-A-T, because they're the same thing. It's that easy. All right, so we got 50 pieces. I'm not setting up a proportion here, so I do want to write the units per 5 students. It's very easy to do that division. You're going to get 10, and that's 10 pieces over students, or 10 pieces per student. And I think that makes sense because student 1 gets 10 pieces, student 2, student 3, student 4, student 5 get 10 pieces. If you add 10 plus 10 plus 10 plus 10, you get 50. How much candy I had in the bag? But uh-oh, I forgot to I didn't distribute my digital M&Ms before class. I didn't do it on time. And all of a sudden, right at the start of class, 20 more students show up, which is a bit exaggerated for this because half of y'all aren't watching live, and that's okay as long as you're watching. But let's just pretend I had 20 more students show up. And so I'm not actually I'm going to say, all right, well, the people that I was giving the candy to, give it back to me. I know, that stinks. You'll still get some, but you're probably going to get less, right? If I got to give candy to 20 more students, that means everybody's got to get less because I only have 50 pieces of candy. So hopefully nobody ate any. Hopefully nobody licked their fingers for various reasons, especially now. So now how many students, excuse me, now how many does each student get? And we're going to stop right here for now. Let's worry about this last bit later. Let's not put too many questions in our head at once. So we got 20 more students, not 20 students total. So our ratio of pieces to students, why did I do double colons there? That was weird. All right, so now we have 20 more in addition to the 5 we originally had. So it's 25 students, excuse me. So it's 50 pieces to be distributed over 25 students. 50 divided by 25 being 2. So now it's 2 pieces per student. And you're like, why even bother? You're just going to give me like a taste of an M&M. At least it wasn't 100 students, because then you'd only be getting half. And I don't feel like cutting M&Ms in half today, especially the digital ones. Okay. So what's the point of this? What's the point of this having some M&Ms, having a small amount of students giving them, taking them back, then having a large amount of students and redistributing them? This is the idea of a concentration. 10 pieces per student is the concentration of candy to students. This is a concentration with a different population. 2 pieces per student. So a concentration is a rate. I'm going to say it 2 more times. A concentration is a rate. A concentration is a rate. It's a rate of something that you have to distribute amongst a population, maybe a population of people, or maybe an object space. So maybe a volume of water or a surface area of something like that, or something like that. I have to say not of. Okay, so now let's get to the second part of this. I'm underlining the wrong thing. If you multiply the number of students and the number of candies each student gets, what is the answer and is this consistent? So I'm asking you to do something very specific. I'm sure you're not surprised. I want you to multiply the number of students and the number of candies. So we'll have case A, which was the top one. So that we're going to multiply the number of students, which there were 5 students, and then times the number of candies each student gets. The number of candies each student gets is the rate, 10 per student. Making sure we're doing our math accurately, we're setting up our fractions accurately, units in correct places, anything after a per goes in a bottom. Students cancel, 5 times 10 is 50, and you get 50, and the units that are left are pieces. Okay, well, how about scenario B? In scenario B, we now had 25 students, and the rate of candies per student was 2 pieces per student. I don't just say 2 pieces because then your students wouldn't cancel and you'd think it's 50 student pieces, 50 pieces students. That sounds weird, doesn't it? It doesn't make sense. So you can't miss anything. Students cancel like this though, and you get 50 pieces. And that was a weird spelling, it looks like. P-I-E-C-E-S. Is this consistent? 50 pieces under case A, 50 pieces under case B. It is consistent. What is the point of all of this candy nonsense? What's the point of this concentration stuff? Usually when we talk about concentrations of something, it's not as fun as candy and students. We're talking about a pollution over a volume of gas, or a water pollutant over a volume of water, or something like that. Or maybe a concentration of just any kind of chemical in a bed of water or some other thing. You can talk about the concentrations of lipids or fats in milk. You got your 2% milk, your whole milk, which is 4%, your 1%, your 0.5%, your 0%. So you can talk about the concentration of fat to the milk in that situation. So in the previous problem, we were using pieces of candy and students. It is literally the same concept as if you use any of these more complex sounding types of things. So the concentration, which is a rate of an amount per unit of volume. So above our quote volume was people above. So volume doesn't have to be a literal volume. It can just be the amount of the thing you've got to give the other thing to. So a concentration, which is a rate of an amount of candy per student, or an amount of fat per volume of, say, water or liquid. So if you take the concentration times the amount of volume, which was this thing right here, these two A and B scenarios, this was the concentration times the amount of the substance. I have it backwards, actually. The first thing is the volume. The 5 students was the volume. The 10 pieces per student was the concentration. And same thing here, the 25 times the 2, that was the volume times the concentration. So if, where did I go? If you only change, I'm sorry, the concentration times the amount of volume should give this the total substance in the liquid, which is exactly the same thing. This 50 was the total substance. This 50 was the total substance. Because you have the same amount of things to distribute amongst either a smaller volume or a larger volume. So if in one scenario it's 2 pieces per student, the other scenario with less students, you're going to get more. So if I just say, all right, I've got 50 grams of fat, and in one case I've got 1 gallon, and in another case I've got 2 gallons, then that means there's going to be a higher concentration of fat in the thing when I toss it in the 1 gallon bucket versus the 2 gallon bucket, which is how you end up with your whole milk versus your 2% milk, essentially. I mean, they filter it versus just actually placing it in, but you get the idea. So this is the concentration formula. This right here is this right here. If you take one scenario's volume times its concentration, if you don't change any of the parameters, you just have more or less people, more or less fat, more or less liquid, whatever, that product has to be the exact same thing as the other scenario's volume times its concentration. So this particular product, the left and the right side would match, and what do they happen to equal? They equal the total amount of the substance, so the total amount of fats, or the total amount of poison, or the total amount of whatever it might be, the cleaning agent. You can talk about so many different concepts here. All right. What page was it? Page 137. How are we on time? 20 minutes. Not that, this. Page 137. So again, I will admit, in this course, this is not something that we are going to repeatedly see over and over and over. I'm very honest about what we'll see over and over and what we won't. We see ratios all the time. It never goes away the entire semester. We'll see the concept of proportions pretty much until we hit chapter 6. And then that idea is still just extended into a higher concept, kind of like inverse proportions as a higher concept. So while we won't really see this much again, it is still an important idea. And now for question 1, we're not going to do all of question 1. We are going to skip mainly A, B, and C. We're going to skip A, we're going to skip B, we're going to skip C. This is just an alternate way of kind of getting to the same point, but without any rhyme or reason. That's what I was trying to say. It's just us arbitrarily saying, well, let's do this and then do that and do this and then do that. So let's go straight to trying to apply the thing we were just talking about so we don't forget it. So this is the concentration equation, but with more appropriate letters for this problem. Why do we get to use it? Well, let's think about it. Your roommate walks at 3 miles per hour and it takes her 8 minutes to walk to class. You, however, have the same class but walk at a much faster pace at 5 miles per hour. 5 miles per hour is hardly a walk. That's a jog for most people. In fact, I would say for most people, that's a run. 4 miles per hour is about the speed, the rate of distance versus time, not just time. 4 miles per hour is about the speed for most people, where it starts getting really challenging to, instead of just power walk, to actually start jogging. And the difference between power walking and jogging is jogging, you'll have both your feet in the air at some points, whereas power walking, you always have one foot on the ground, no matter when it is. And I've seen some fun little arguments over those two things before. It's kind of silly. Either way, not the point of the problem. So you walk slower at 3 miles an hour and it takes you 8 minutes to walk to class. But your roommate, who walks much faster at 5 miles per hour, maybe a really solid power walk or a mild jog, how long will it take to get to class? This is actually a concentration idea because you both have the same distance to cover. That's the same, quote, volume, if you will. So you have the same distance to cover, but one of you is going to cover it faster, which means that they should be able to do it in less time. If you increase your speed, it should take less time to get somewhere. This is not an idea of a proportion. Concentrations are not direct proportions. Again, concentrations are not direct proportions. They are not proportions. You can't use y equals kx for this stuff. You can't go fraction equals fraction in the traditional sense of proportions. Notice I said they're not direct proportions. They're actually inverse proportions, but let's not get into that at all. So we're going to take the 3, the 8, and the 5 and just plug them in here. I am going to use the annotate for just simplicity's sake. So there's 2 cases here, and that's what the little 1s and little 2s are for. So case 1, case 2. Case 1 is you. You are case 1. So this 3 miles per hour, that's your rate 1. This 8 minutes, that's your time 1. All right, then the other person, oh, I'm sorry, case 1 was the roommate. Case 2, that's you. You walk faster at 5 miles per hour, that's rate 2. So you is case 2, and I said that funny intentionally. So your goal is to find how long it will take for you to get to class, which we'll call T2. So we're just plugging those numbers into the concentration equation. Again, this is not a concept of proportionality. And you might try to use this as a proportion. You might say, oh, okay, well, 3 versus 5, that means the 8 minutes is going to go up by 5/3. And you would say that answer ends up being 13.3 minutes. If you're walking at 5 miles per hour, you're walking faster than your roommate. Let's just say you both started at the exact same time. You started walking. You're going to get ahead of your roommate instantly. Why would it take you 13.3 minutes to get to class if you're taking the exact same path and your roommate's walking slower? That would make no sense. So you go, well, wait a minute, this can't be a proportion. That makes no sense. Throw it in the trash can. Maybe it's this concentration idea because we have the same amount of thing to cover, the same amount of distance, our quote volume in this instance, but we're doing this at different speeds. So those different speeds are kind of like the different amount of students in that last case. All right, so R1 is 3, so we're going to plug in the 3 here. Now here's what's cool. The rate was in miles per hour, the time is in minutes. Those are not the same units. So you go, well, that stinks. I need to convert one of these things to miles per minute, or this to 8 hours. I'm sorry, or this to hours, which would be less than an hour. But the awesome thing about concentration equations is if one thing has this particular pair of units, so R1 has a particular pair of units, that means R2 will have the exact same pair of units. You don't have to actually manipulate them. If T1 has a different type of unit, then T2 would just match the same units as T1. So that's what this first problem was actually kind of doing. It's going what we would have done before we got to this section. It's saying, well, convert the minutes to hours because these aren't the same thing. Then you can figure out how far away class is based on using those two numbers, multiplying, dividing them, however they make sense. And then you can, figure out, all right, well, if that's the distance, how long is it going to take your classmate to do it if they're going to go at that speed? But instead we're doing it this way. So I'm not going to even put the units, just the 3. The T1 was the 8, so that's times 8 equals the R2. We know it's 5, but we don't know the T2. That's our unknown. Well, 3 times 8 is 24, so that's 24 equals 5T. That does not look like 5T. You're then going to divide both sides by 5. And then 24 divided by 5 is going to be 4.8. Yeah, 4.8. I don't want to have to pull the calculator up for that. So we get 4.8 is equal to T2. T2, the first time was in minutes, which says that this is 4.8 minutes. Again, yes, one of these things has hours, one of these things has minutes. In terms of actual dimensional analysis, it feels like it wouldn't work. It feels like you'd have to cancel everything, but the beauty of this concentration formula is that you don't have to. The time in one thing is the time in another thing. The rate in one thing is the rate in another thing. So it takes your roommate 4.8 minutes to walk to class, which is the exact same answer you would get if you do it by method 1. Yeah. So this is awesome. Does it make sense? Well, it took your roommate 8 minutes at a slower speed, so you're going faster because you're late, I guess, maybe, or you just naturally walk faster. And that's me. So 4.8 minutes, that's less than 8. So that's in the bounty of making sense. Now, again, yes, the units are just automatic, so you can't use them as a gauge of making sense, unfortunately, but this is still a great tool to have up your belt. And I'm going to need to clear my screen. So if you don't have the notes yet, remember, go to YouTube, pause it. All right. Problem 2 and 3. Problem 2, you have a fixed budget for flooring your new home. One type of flooring costs $4 per square foot. I feel like this problem is dealing with my real life right now. And that $4 per square foot covers 89,280 square inches using your budget. Oh no, one of these things is in square feet, the other is in square inches. Thankfully, because this is going to be a concentration style problem because we still have the same amount of space to cover, no matter what scenario we're under. So we don't have to worry about the unit conversions. We certainly could, but it's going to be extracurricular. All right, so $4 per square foot will cover 89,000 square inches, which again, you could convert to square feet, but we're not gonna. But you go, well, I like the $4 per square foot, but this $6 per square foot, this fancier one, this more expensive one also looks really nice. And they say, well, how much flooring would you actually be able to cover on your budget? So on our budget, they didn't say how much money we have, but we know that we can cover this much volume of flooring, if you will. And again, that's a poor name for that, which is why I said it so exaggeratedly, because it's a true surface area, or just area, if you will, but we can call it a quote volume for the concept. All right, so if you buy more expensive floor, obviously you're going to be able to buy less flooring. So we're going to be able to buy less than about 90,000 square inches. But how much will we be able to cover? So maybe we got a house and we know that this house is, let's say, 50,000 square inches. So the first one, the more budget priced one, we can definitely cover the house if it's only 50,000 square inches. But what if we were to buy the more expensive one? So the $4 per square foot, that's the first rate. How do I know it's a rate? Because it has the word per, it's got two different types of units. Then A1, that's the area, that's A1 there. The more expensive flooring is $6 per square foot, that's the second rate. How much flooring will we cover? Well, that's A2. So we just jam those numbers in the formula. R1 was the $4, skipping the units here because it'll look really weird otherwise. The algebra will terrify you with all those units in place. We don't like to solve equations with units in them, and that's what this is. This is an equation. Before, we were just doing what we call expressions. It's not a left side equals a right side. We were just taking a number and multiplying or dividing things. All right, so 4 times the 89,280, and then equals to the R2 was the 6, and then times our A2. I am going to plot the calculator this time. Otherwise, you might not trust my numbers. So we're going to go 4 times 89,280. So that's the left side. That is going to be 357,120 equals 6 times A2. We're then going to divide both sides by 6. Divide by 6. Come off the annotate. And we get 59,520. That's our A2, but don't just say that's the answer. 59,520 is not the answer. What was the first area measured in? It was measured in square inches, so this is in square inches. So it's 59,520 square inches, or you can go 59,520 inches squared like that. So if you had a house that was 50,000 square inches, yes, you would have enough to be able to buy the pricier one. You would have less wiggle room because you're going to make errors. You're going to have to make cuts and stuff. So waste, usually say get to 10 or 20% more. So you're getting pretty close to, you know, if you make too many mistakes, maybe you'll have to go a few bucks over budget because 60,000 would be 20% of that. 20% more than 50,000, that is to say. All right, finally, my favorite one. Number 3, just do that. Oh, nope, can't do that. Let's put it over here. Good enough. Janine eats a quarter of a cup of oatmeal per day, also known as 0.25 cups per day, and a container lasts her 36 days. This is her by herself. So her husband starts eating half a cup a day. How long will the container now last with both eating cereal each day? So, January and a little bit of change into February. Janine buys a box of cereal. She eats oatmeal. Oatmeal, cereal, same thing, right? And she's eating a quarter cup of oatmeal per day, not a lot, and it ends up lasting her 36 days. All right, so box 1 of oatmeal finishes. Janine or husband goes to the store, maybe together, maybe separate, doesn't matter. And he or she buy more oatmeal. But the husband goes, I'm going to get on this oatmeal train. So it's not just Janine eating oatmeal, it's Janine and the husband eating the oatmeal. And they say, how long will the container now last? So here is where people make their mistakes. They go, all right, this quarter of a cup per day so that's the first rate. So that's our R1. And I'm going to go ahead and convert it to a decimal just to make things a little easier. It's 0.25 cups per day. The husband eats half a cup per day. So that's another rate. That's the husband. That's R2 equals, and that would be 0.5, question mark, question mark, question mark. And I'm going to go ahead and say that no, that's wrong. That's wrong, and I'm going to show you why it's wrong. So let's, for red, pull out why this would be wrong. Oh, by the way, I forgot to mark what T1 was. That'll be correct. T1 is 36 days. We want to know what is T2, the time of the husband eating. Actually, no, that's not right. It's not just the husband eating, it's the husband and the wife eating, which is why what I'm about to do is wrong. So they'll say R1, that's the 0.25. T1 was the 36, so times 36 equals R2, we said is 0.5, but I'm telling you it's wrong. Just bear with me and we'll see why. All right, so 0.25 times 36 is going to be, what is that, 9? Yeah, that's 9. So that's 9, and then equals 0.5 t. Just divide both sides by 0.5. I'm not going to change colors. And 9 divided by half is the same as 9 times 2, but you got your calculator, so you don't need to know that. And you get 18 is equal to T2. But it makes no sense. Why does this make no sense? Because it took 36 days for Janine to eat this oatmeal by herself. If the husband was eating by himself, he's eating twice as much, so it should take half as long. If you're only eating a half a cup a day, it would take 18 days. But it's not just the husband, it's Janine eating a quarter of a cup and the husband eating half a cup, which means they're eating 3/4 of a cup or 0.75 cups a day, which means it will take less time than half of the original time. So a lot of people will say 18 days makes sense because it's less than 36 days, but when you think about it deeper, yeah, it's kind of ballpark, but because it's the two of them eating, it was the 0.5 that was wrong. That is not the consumption rate. So let's actually do this correct now. So correct, R2 is actually 0.75 per day. And that's what 1/4 plus 1/2 is. That's 0.25 plus the 0.5. This is the actual consumption together because they're both eating. It's not just the husband eating a half a cup, it's him eating a half plus the wife eating a quarter. So the correct problem is 0.25 times 36 equals 0.75 times T2, which you still get 9 on the left, but now you'll be dividing by 0.75. Again, not going to change the color. 9 divided by 0.75. It's going to be 12. So that says that 12 is equal to T2. The time was in days, so it's 12 days, and that does make sense. All right, we only have a few minutes left, so I'm going to skip number 4 and go straight to number 5. Clear my screen. I'll give you another 10 seconds. And again, I know that this problem right here, a lot of people would think the 18 makes sense, but that's because this has an extra little convoluted piece to it, the fact that you have to add those, but they don't tell you that. You have to really think, all right, they're eating together, which means it's not just the husband eating in the second scenario, it's both of them eating, which is why I added those to get that 0.75. All right, now let's clear, scroll. Okay. 4 and 5 are pretty similar, but 4 is in scientific notation, so it would take me a little longer than the 6 minutes we have left to get into all that. So let's just go straight for 5. We were never going to do 6 because it requires systems of equations, which is not a math topic that we assume you've had in here, believe it or not. All right, so you have a solution mixed at a concentration of 5 grams per milliliter. Oh, good Lord, solution, volumes, mixtures of concentrations? This is terrible stuff. I don't understand this. All right, You have a class and you're giving them 5 M&Ms per student. That's the same thing here. 5 M&Ms per student. That's the rate. It's just a rate. Don't worry about the concept. And you need 100 gallons mixed at 4 grams per milliliter. Not only does this question not say, what thing are you finding, it asks you a true quantitative question. What do you do? Huh? What do you do? What are you talking about? Let's ignore the question for a second and let's just try and solve the problem. So we're a store and we're a chemical store, and our chemical, we have a volume of liquid and the concentration of the chemical in it is 5 grams per milliliter. So every milliliter of this liquid has 5 grams of this substance in it, maybe alcohol, maybe thieves cleaning solution, so thieves agent, whatever, I don't know, doesn't matter. Rubbing alcohol, whatever. So every milliliter has 5 grams of that cleaning solution. Well, unfortunately, a customer comes in, Bob. Bob says, "Sir, good day. I need 100 gallons, but your concentration is a little too strong for my needs. I need this to be a little weaker. I don't want 5 grams per milliliter. I only want 4 grams per milliliter." That's what the what do you do aspect, that's where the what do you do aspect comes into play. The fact that the concentration we have to offer is too strong for our customer. So that's the what do you do, but again, that'll be the last bit. For now, 5 grams per milliliter, since that's a rate, so that's rate 1. The 4 grams per milliliter would be rate 2. And then you have to be careful. Does the 100, is that going to be, and by R, they're using C, so let me just use the same letter, C1, C2. Rates are concentrations. I said that earlier. The letters are interchangeable. I could have written that as R1 times V1, R1 times V1. So the 100 gallons, is that the first scenario or the second scenario? Well, your store offers the 5 grams per milliliter, and the customer comes in and wants 100 gallons. So the 100 is with the customer, so this is V2 actually, not V1. We're trying to figure out what volume we need, to get for them. So the equation goes 5 for the C1, the V1 is the unknown, equals the C2, which would be the 4, times the second volume, which was the 100. Well, 4 times 100 is 400, so we get 5 times V1 equals 400. We will then divide both sides by 5. And then that's going to go in, 80 times? Yes. So the volume of liquid that we need to give the customer is 80 what? Well, the customer wants 100 gallons. That was the units of their volume. So our volume needs to be 80 gallons of our liquid. So that's what we need to give the customer. Hold on. The customer actually wants 100 gallons. At the concentration we have behind the counter, in order to get the total amount of the cleaning agent, the thing in there at 5 grams per milliliter, we only need to give the customer 80 gallons because it's stronger than what they need. So in order to get the total cleaning agent, they want 100 at a weaker solution, so we only give them 80. But the problem is the customer says, don't give me 80 gallons mixed at 5 grams per milliliter. I want 100 at 4 grams per milliliter. So what do? You need to dilute the liquid that you're giving them. You need to give them 80 gallons of what you have in stock, but since they want 100 gallons and it to be weaker, you just add water. How much water? Well, you got 80 gallons of the stronger stuff. If you need to give them 100 gallons of the weaker stuff, you add 20 gallons, and that is how you will achieve it, by putting 20 more gallons of just pure water, something that does not have that concentration. You will dilute the substance, you will get them the volume they want, and it will be at the appropriate strength since we use the concentration formula to get there. That is the same concept to problem 4. So problem 4, I'll give you the answer if you'd like to try it. You'll have to look up the scientific notation with negative exponents if you're a little rusty, but negative exponents just mean the decimal goes left. So for instance, and I only have like 30 seconds to talk about this. Oops, nope. Clear first. Clear. So they give you 10 to the minus 3, which means you move a decimal left 3 times. They give you 10 to the minus 4, which means you move a decimal left 4 times. When you end up solving this, if you want to try this on your own, you will find that V1 equals 10. But this is another scenario of they want 100 gallons of something, or excuse me, 100 liters of something, but then you only need 10 liters from behind your counter. So you add 90 of water. Add 90 liters of water to give them their 100 liters that they want. I'm sorry, not liters, milliliters. Milliliters. The concentration was measured in a per liter, but the volumes are measured in milliliters. So I will say this one more time. In terms of this course, this is not a topic that's going to pop up in chapter 4 or 5 or 6 or 8 or 9 or 10 if we actually get there. However, this is still a very cool concept that you can use in the real world.
And on that note, we will call it there. So that was week 5, lecture 1. Again, just leaving the whiteboard up for the last little bit of time in case you missed it at the beginning. But remember, you can always catch the replays if you come in late. They just aren't always available immediately after class. So we got some Mymathlab homeworks, we got some Excel homeworks, we got a discussion board or two, we got a quiz or two. If you've been keeping on pace, most of these assignments due today you should have already finished. If not, make sure you finish them today. The ones due on the 22nd, of course. And then go ahead and get started on the rest of them. Please remember that I will not be here live on Zoom on the 24th, but we will still have a full recorded class available on YouTube. So there is still a full lecture, hour and 45 minutes, hour and 50, like we typically keep it. And also, if you wanted to go ahead and watch it Wednesday evening, I should have everything up by Wednesday evening, no later than 8 or 9, if I had to guess, because I'm going to be working on that all day tomorrow. Besides that, I hope we had a good session today. I hope we learned some stuff. Remember, next time we're going to talk about the midterm exam, which is going to cover the first 4 chapters. We'll talk about that in great detail. We'll also talk about the project. We're going to talk about that in great detail, about where you can find the files, what to do, all that good stuff. But for now, have a good one. While I will not personally see you on Thursday, you can always email me if you have any questions. And then I will see you again on Tuesday, the 29th. So take care, everyone. Have a good day. Have a good week, ultimately.